Hello everyone. This course is dedicated to introduce you guys to the concept of fractals and how to write them in JavaScript. So what you're seeing on the screen right now is called the Mandelbrot set, and it is one of the fractal. Now fractal are, well, to put it simply, it's a pattern that kind of includes itself within itself. So you can see that there are some recursive patterns, which means that there are some patterns that can repeat itself kind of infinitely, but changing a little bit every time. And it's actually infinitely complex, so it is actually impossible to compute technically. So what you're seeing right now is a very close representation of Mandelbrot set. So we're going to be talking about this fractals, and as I said, you guys will hopefully know at the end of this course how to code them on JavaScript and visualize them. So what are fractals? Well, let's go to the other tab. So just search fractals on Google. So to me, this definition is pretty much accurate. So a curve or geometric figure, each part of which has the same statistical character as a whole. So for example, something like that is known as the Sierpinski triangle. So that's a GIF, not a good one. I think this is a GIF as well. Well, you can see that it has the same structural pattern as a whole. So basically, you can see that, for example, the single triangle contains 3 copies of itself, and so on. So it's infinitely complex. Now, obviously, I'm going to be talking about why are these important and why do we even care about these. And that is actually a very interesting topic. So for example, when you go right down here, you will see that fractals actually represent nature incredibly well. So this is natural phenomenon with fractal features. So for example, it's a broccoli, and it's a Romanesco broccoli. So as you can see, it has a very fractal pattern, which means that it kind of has the same pattern within the pattern. So for example, a snowflake. So it's a frost crystal. Sorry, it's not a snowflake. But you can see that this whole thing kind of looks like this single line there, which is kind of incredibly complex. Also, this part looks like a tree. So in fractals, we know that trees are a bit of a fractal as well. So you can see extremely complex, and it kind of you can see it kind of contains itself, contains the pattern of itself within itself. So there are a few examples of that, and we can use this to simulate the world in one aspect. So whenever you create games or create computer graphics, it really takes time to create something that is incredibly accurate to nature. Now, fractals can come in really handy. So for example, when you're generating a landscape, something like this, which is it's actually a pretty simple fractal pattern, but it kind of creates this very realistic looking mountain. Same with trees, and we say that clouds and different organs in our bodies are also fractals. So that's very interesting. We can have the formal definition of fractals. It's a self-similar subset of Euclidean space whose fractal dimension strictly exceeds its topological dimension. So I'm going to be explaining about what fractal dimension is. Actually, there are a few types of fractal dimensions. This is the most famous one. It's the Hausdorff dimension. So it honestly, it really changes the way you look at this world, because this is the coastline of Britain. This is a very famous example that we really like to use. It's something like the teapot for 3D graphics people. They really like to play with teapots. We like to play with the coast of Great Britain. And we like it because the coast of Great Britain is incredibly complex, and at the same time, it really has a fractal pattern, which is really surprising because you don't expect something like that to really occur in nature. And that's what Benno Mandelbrot, who's kind of the founder of Fractal. He's a very good guy. I read some books of him. he explains about a lot of things that he finds within his research. So we're going to get into those details on the future videos. And on the first video, which is this one, we're going to be just start the coding part. And as I said, I'm going to be using JavaScript. So I assume that you guys have basic knowledge of JavaScript. Now, whenever we're visually drawing and representing all these fractal, beautiful patterns, we need to first know about the concept known as recursion. So let's just get to the console. This is, hopefully you guys know that this is where you can run JavaScript. It's probably the easiest place to run JavaScript because you can literally right click and click inspect. Okay, and I get rid of that. Okay, so let's just, let's make sure that this is JavaScript. We're just going to be printing some word. Well, this is the first thing that everyone does. So we know that this is JavaScript. That's cool. Now we can make a function, which is something that I think you guys are familiar with. So maybe just print something like f. no, sorry. Okay, something like I am f. Okay, that makes more sense. So whenever I go f, it prints that because it's a f function. Okay, so when we say recursion and when we say that fractals are recursive, it means that fractals contains itself within itself, which each of those obviously contains itself and so on, right? So usually when we draw or simulate fractals, we make this thing called recursive function. So instead of doing something like this, what we're going to do is we're going to call another f, right? So I really hope that whenever you do something like this, it will destroy your code, because not your code, destroy your browser, because it's going to get stuck in an infinite loop, basically the same as doing something like while true do something. So what we can do here is, because this is a very useless code, and I mean, actually, this is how you should actually make a fractal, because as I said, fractal is infinitely complex, right? So this is a right way, but you know, you don't want to burn your CPU, so you would want to tell them to stop at one point. So so I hope you can read this text. It might be pretty small, but when we said it's a Sierpinski carpet to level 6. Now level 6 means it has a complexity of level 6. So it's extremely complex in one aspect, but at the same time it's not infinitely complex. It's just 6 layers of complexity. So that's where we use this thing called the depth, okay? So, okay, yeah, sorry, it might be confusing at this point, but trust me, this is going to get familiar throughout the course. So let's say you pass 10 to depth. So usually you pass a number to it. And this depth obviously doesn't change. So when function 10 is run, and then it calls function of 10, which calls function of 10, so it's just another infinite loop. But what if we decrement this value every time? So in that case, first, when this function is run, so obviously maybe we need a way to print this, something like depth. Now, still, if I run this, it would crash, so I can't do this yet. But still, I hope you can see that if this function is run with 10, it we're going to print 10, then it we're going to print 9, and then 7 and 6, and then so on, infinitely, towards negative infinity. Right, I think that's clear to you, because when that's 10, then that becomes 9, so 9, f of 9 is called, which invokes f of 8, invoke means just execute, run, which invokes function of 7, and then function of 6, function of 5, and so on. So we would want to tell them to stop at one point. So usually we will do something like if depth is more than 0. So what this does is obviously when you call this, it will run, right? 10 is more than 0. So, but then it will going to run 9, and then you're going to run 6, 8, 7, 6, 5, 4, 3, 2, and then when it reaches to 0, this condition will not meet, right? So that deepest function that is invoked, so you can think of recursive function as a kind of a nested function, right? So obviously, if you break that, so let's say I run 5, right? This is what happens. So as I said, the moment this depth becomes 0, it will just stop invoking. So it will stop at one point. So maybe some of you guys are still confused to what exactly a recursion, and I think that's normal because it's a very confusing subject. But still, let's just start with the actual coding part, because I think that way you guys will slowly get familiar with the concept of recursion. So first, for our first video that we're going to be doing, which is this one, we're going to be making the contour set. So first I thought of making the fractal tree because it's a very simple yet beautiful shape, and obviously it's a very, it has a fractal pattern to it. But in order to do this, we were going to need to do some vector calculation or even trigonometry stuff, and I thought that would be kind of confusing. So first we could start from contour set. So let me explain what exactly I want to do here. So imagine a function that draws a rectangle, and let's say each of these height is 5. Then imagine that this, this coordinate is 0, 0, and let's say the length is 400, whatever. Okay. Now, so this function is really simple. It just draws a rectangle. So that's simple. But imagine that this function invokes itself within itself. So let's say this function takes in parameter of x, y, and let's say the width, and then, well, not the height, so I think that'll be fine. And then let's say it takes in the depth, which is the indicator to when to stop invoking itself, which you saw just now on the demonstration I did on the console. And so imagine that this guy calls itself, so something like that. And then let's say it calls itself, but instead of simply passing these value, it adds 10 to the y coordinate, and then let's say it just keeps the width, but then decrements the depth. Yeah, something like that. So in that sense, in that case, that's going to be 0, while this point is going to be 10, and then obviously that's going to be 5. But notice how, so let's say if the depth here was 6, and the depth here is going to be 5. And then so on, so on. So you can notice that this function kind of continues until eventually it reaches to the depth 0, and it kind of stops executing more functions. So there's nothing below here. Right, so that's pretty simple, actually. But first we need to implement that. So we're at Visual Studio Code. This is going to be the place where I'm going to make my project. So let's just go ahead and create index.html. And also index, well, we can name it something like contour.js, because we're going to be making the contour set. So on the HTML, let's just go ahead and add the HTML tag, head, then the body. So again, yeah, I assume that you guys have somewhat knowledge of HTML and JavaScript, but these two are only the thing that I'm going to be using. So this time we're going to be using our canvas to draw anything on it. Let's just go ahead and add some style, background color, black, yeah, that works. Yeah, if it's white, we won't be able to see it. And the width, just, oops, something like 400 pixel. And same with the height. Not sure why is it doing that? And let's just load the script. So in the script, we're going to be doing the source is equals to contour.js. Now inside here, let's just I don't know, alert something so that we'll know that this file was loaded. So maybe something like 0. Let's just go ahead and save this, save that, and we can click Open Live Server. Then we can run the HTML. Okay, so we just alerted stuff, so we're good, and there's the canvas right there. So now we should actually start drawing the contour set. So let's just go ahead and remove this alert and start with loading the canvas from the HTML. So it's going to be document dot so let's go ahead and just remove this and load the canvas into the JavaScript. Let canvas is equals to document dot query selector, then put in a canvas there. And then we need to get the context, which is going to be what we're using. So let's just go ahead and remove this alert, first of all. And we need to load the canvas, first of all, in order to draw some stuff in. So we're going to do canvas is equals to document. So first, let's just go ahead and remove that and load the canvas into the JavaScript. So we're going to do document dot query selector. We're going to put in canvas in there. So basically, this is going to select the first element that meets with the canvas criteria. And then we need to create the context. This is going to be what we're actually using to draw anything on the canvas. Otherwise, we can't do anything. So get context, then put 2D in there. This is going to be, so whenever I want to draw a rectangle, we're going to be doing something like context.rect. Okay, and then, well, we should actually start making the function. So function, so maybe the rectangle that we were doing, function rectangle. And then inside this, so as I said, this should be kind of a recursive function. So we're going to need a def first of all, and also we were going to need, well, let's say, well, the width of the rectangle, or maybe, you know what, the x coordinate, the y coordinate, and then the width of the rectangle. So these 4 parameters. The reason I didn't put height is because both for contour set and the thing that I'm trying to make right now, the height is always consistent, right? So I'm just not going to do anything with that. So let's just go ahead and, well, let's make it so that it only happens if the depth is more than 0. So it works just like a while loop. Maybe you can think of it like that way. And then inside here, you can do, so ctx dot fill rectangle. So let's create a rectangle that's filled inside at x, y, and then width. And let's make the height something like 5. That'll be good. And then in here, what we need to do is we need to call itself, right? So this is the main, I guess, the thing that happens whenever you're making any fractals or any recursive function. We just do call itself within itself. But obviously, we need to indicate that at one point to stop. So we were going to add the depth, and we were going to decrement it. Right. Okay, that's, yes, so x, y, yes. And obviously, y needs to be changed as well. So let's say we add 10 every time. Now, we were going to do we need to just run this function. Let's say at 0, 0, maybe width is 400, which is the full width, and then the depth is going to, let's say, 6. Okay, by the way, I forgot to mention that on programming Canvas, the y coordinate, the positive side is downwards, while a normal mathematical graph system, positive is upward, right? So on the drawing that I did just now, I said that the y coordinate will going to be determined based on the depth, but this time we can't really do that. So what we need to do here is just create the y variable so that it's much easier to both read, debug, and trace stuff. So let's just go ahead and save that and run it. Okay, so let's see what happens here. Let's just reload this, and it doesn't draw anything. Let me check why. Oh yeah, and then yeah, sorry, I literally forgot to set the color of the rectangle. So just now it was invisible because the default color is always black. So let's just go and make that white, and let's see if it works. Okay, so it works. It works perfectly, as you can see. You know, all these things are there's 6 tapes in total. So let's just check the contour set that we're interested in. So it looks like that, and so what we created just now is pretty much linear, as you can see. Each of the function only equals a single function. But what we want to do here, especially when you're making fractals, you're going to need to run multiple functions for each individual function. So so this function, so right now it's that the top function only calls one function, but in this case the top function calls 2 other functions, and so notice that there are 2 things changed, and one of them is obviously the length of each of these segments. All of these are 1/3 of its original of its parent's length, and then its x position is also changed. So for example, these guy's x position is exactly the same as the parent function's x position, while this guy's x position is 2/3 of this initial position. And then the same goes for all of these. So for example, this is exactly the same position as this, while this is exactly the same position as this, but plus the length of this times 2/3. So I hope you can see this pattern. So let's just go ahead and modify our function so that instead of running a single function, it runs 2 functions. So as you can see, right now it only runs a single rectangle. It only runs itself once. So what we could do here is we can run it twice, and then, as I said, so this guy's x position is the same as its parent function's x position, but for this, you need to add its length or the width times 2/3. Okay, so that's going to be simple. And then for its y position, it doesn't change, and then for its width, it becomes 1/3. Okay, now let's see if that works. So let's go back to the previous tab. Oh, there we go. So it works. Let's just zoom in a little bit. Yeah, so as you can see, it works now. So it's just simply that instead of calling itself once, by calling itself twice, it creates this relatively complex shape. Well, this is actually the basis of the fractal programming, because it just means that it kind of changes itself a little bit and then runs itself multiple times. So yeah, so now hopefully it's more clear, it's more solid for you guys how does these work. So now that we've finished our first contour set, maybe some of you guys are still kind of confused, and I don't really blame that. I was really confused at the beginning too. So maybe from the next video, also you guys can get more familiar with all of these concepts. But now that we've made the contour set, I think it's pretty obvious that, for example, something like this is not that difficult and not that complex, because you can see that, imagine if the single branch, again, is a function, then this branch calls itself twice, which each of those branches also calls itself twice. then 4 of them, and 8 of them, and then kind of grows exponentially and grows exponentially complex. And not only that, for example, yeah, these things, I think most of these things looks much more simpler and much more clear in your mind, hopefully. And then soon, at the end of this course, hopefully, we'll be able to create something as complicated as Mandelbrot set, or even these Julia set, or even these strange attractors. So yeah, this is something really interesting. So yeah, let's see you on the next video. And thank you for watching. Bye.